Welcome to another lesson of the course, Curves in Engineering and Architecture. We are in the second part of the course, namely Curves in Road Safety. In Module 4, we introduce a problem in road safety engineering that is solved with the help of curves. Lesson 4.2 is about which properties do transition curves need to have. Remember, our problem was to design comfortable and safe highways and railways. To do that, we look for geometric design consistent with drivers' expectations. Geometric road design comprises horizontal and vertical alignments besides of the transversal section. Our problem deals with horizontal alignments, but we also treat the case of vertical alignments in Lesson 6.1. We already saw that curvature of a curve measures the size of change rate of its tangent direction. In this way, a straight line has zero curvature, and a circular section has constant positive curvature. Moreover, centrifugal acceleration is proportional to the curvature, so a jump in the curvature will produce a shaking. To avoid shaking, we want the curvature to vary in a smooth manner along the road. Then a transition curve should have curvature that varies smoothly with the position on the curve. The question is, which curves do have this property? If we are moving from one point on the curve to another one, the change on the curvature should be proportional to that displacement. How we can measure this displacement on the curve from one point to another? One possibility is to measure the arc length along the curve that you can see in red color. Another possibility is to measure the corresponding displacement along the curve that joins initial and final points, that is, the length of violet segment. One could even measure the displacement along the horizontal direction, which is colored in black. In the first case, we look for a curve whose curvature kappa is proportional to the arc length L. The equation of this curve will be kappa equal to a constant times arc length. And now, as the curvature is the inverse of the radius of curvature, the equation says that the radius of curvature r is inversely proportional to the arc length, as you can see in this image. This curve has a double spiral shape, and it is known as clothoid, a name given by Cesaro in the 20th century because its shapes reminded him of the thread wound around the spindle, and in ancient Greek mythology, Clotho was one of the three fates who spun the thread of human life. In the second case, we look for a curve such that the curvature kappa is proportional to the length of the curve, say d. The equation of this curve will be kappa equal to a constant times d, and the corresponding curve is called lemniscate. You have seen this curve before in part 1 of this course devoted to curves in construction and architecture. Finally, in the third case, we look for a curve such that the curvature kappa is proportional to the length of the horizontal displacement, that is, the length of the abscissa, say x. The equation of this curve will be kappa equal to a constant times x, and the corresponding curve is called radioid of abscissas. These are oval curves that, in the particular case in which the core is horizontal, turn out to be a lemniscate. Having at least these three possibilities, the clothoid is the most used as transition curve in roads because calculation and field implementation are easy for these curves, as we will see later. The clothoid was used for the first time as a transition curve for railways by the engineer Talbot in the late 19th century. But first work on this curve dates from 17th century in the context of an elasticity problem by Jacob Bernoulli. This problem was solved by Leonhard Euler in the middle of the 18th century. Some years later, the curve was rediscovered by two physicists in connection with the diffraction of light, Augustin Fresnel and Alfred Cornu. Clothoids continue to be the subject of interesting engineering and mathematical studies. Naming the constant present in the equation of a clothoid as a squared where A is a positive number, we will get one different clothoid for each value of the number A. That is, a whole family of clothoids dependent on the number A. All these clothoids are similar in shape, but its relative size is bigger for big values of the parameter A. Now, we need to discover how to effectively use these clothoids as transition curves to contribute to a better road safety. We will do that in lesson 4.3.